Okay, so I created this tic-tac-toe thing, and then so I'm going to just start off by saying play, and then it asks how many players, 1 or 2. So I'll say 1 human, and we'll say the computer will play second. Okay, and so I'll have maybe I'll play in the corner. Okay, so I played in the corner and it goes there. All right, and then so this is what the board looks like after I played. It says O plays 5, so O goes right there. And then so maybe I'll play in spot 7. Sure. Okay. All right, so I played in spot 7, and then so O plays there. Okay, so as far as what the you guys don't have to program perfect optimal tic-tac-toe gameplay. There's only 2 rules that I need you to implement, and that is if the computer can win on a move, it needs to win. Okay, and if it can't win but it can block a win, then it needs to block the win. Okay, and those are the only 2 things, right? And if you pay attention, like if the computer can do that, it's going to be better than most 4-year-olds, right? So if it can win, it'll go for the win. If it can block, it'll block. Okay, beyond that, it doesn't matter. Okay, so where should I play? I should play 6, right? But maybe, okay, so if I play 2, the computer should go for the win. Okay, and it does, right? And so I went there, and the computer goes there. Okay, we can do play again, and then we can say we're gonna have 2 human players, and then now I can go. We can just play silly, all right? And then so X plays at 9 and wins or something like that. Okay, and so this is I don't know. That's what I have as far as the computer. The thing again. Okay, so is this all right as far as how the game is running? And okay, so anyway, we'll it shouldn't be too terrible, but who knows. Okay, let me pause. Okay, all right, so let me clear out our workspace, clear that out, and we'll start today's lecture. Today we'll talk about environments and debugging. My stuff on environments, actually a lot of my stuff comes almost straight from Hadley Wickham's textbook. So especially this environment stuff, I just used his images directly, okay? That kind of shows it. His Hadley's textbook goes much deeper into the details on environments. This I'm giving you kind of like a 20-minute, 30-minute talk on just kind of the basics of environments that I think you need to know. But yes, okay. All right, so environments, that is the data structure in R that powers scoping. Scoping being the idea that when it looks for something, it's going to search this environment. If it can't find the thing that you asked it to find, it's going to scope to a higher scope, okay? And environments allow for that to happen, okay? And so what an environment does is it binds a set of names to values, okay? So you can think of an environment as a bag of names, all right? And so here I've got the names A, B, C, and D, and we want to bind those things to values, all right? And so we can create a new environment using the command new.environment, okay? And this is going to create a new environment E, but most of the time you're just working in the global environment, and that's totally fine. That's like 99% of all people just work in the global environment, okay? And so here we're assigning the value false to A, the character A to be inside this environment, and then 2.3 and so on and so forth. And then so just what this does is it takes the letter A and it stores, it binds it to the value false, or it takes D and it binds it to the values 1, 2, and 3, right? Because inside your computer, it's storing these values 1, 2, 3 somewhere in the memory, but the environment says, hey, this is the name and I want you to bind it to this value here, Okay, and so we can do that. We have parent environments. Okay, every environment has a parent, which is another environment. Okay, and so in these diagrams that I've stolen from Hadley, we're going to indicate that an environment has a parent by putting a little black dot here. So this black dot means it has a parent, and when I have the arrow, it's going to be that parent environment is over here. Okay? This environment also has a parent environment, but we didn't draw the arrow to show where it goes. Okay? Every environment has a parent. Okay? Every single environment. The global environment has a parent. It goes all the way up to the base environment. The base environment has a parent. And the only environment that does not have a parent is the empty environment. That is at the very, very, very top. That is the ultimate ancestor of all the environments. Okay, that one does not have a parent. But everything else, all other environments, you've got a parent. Okay, and so, and the way the scoping goes is that you tell. If you're inside this environment, this is my global environment, and I say look for D, okay, it's going to search this environment first. It doesn't find it. It goes, oh, okay, we're going to go to the parent, and then it finds D over here. Okay, if I told it to find K, and it doesn't find it here, it's going to go to this parent environment, wherever that is, and if it doesn't find it there, it's going to keep going, and it's either going to say, oh, I didn't find that thing at all, it's nowhere to be found, or, you know, here it is, okay? And it doesn't tell you like, oh, I found it in this environment. It's just going to say, okay, here it is. This is where I found it. Okay, it's got to go up the ladder of parents, though. Okay, it's not going to. If you've got another environment over here that's like a cousin, it's not going to find it, right? Because it only climbs up the ladder of parents. Right? There's no such thing as cousin environments anyway. All right. There are 4 special environments, I guess, that you should know are important ones. You've got the global environment. This is where you're going to be doing most of your work. Okay. The parent of the global environment is the last package that you attach with library. Okay, so if you do like library ggplot2, if that's the last thing you did, that's going to be the parent of the global environment. All right. The base environment is the environment of the base package. Okay, this is kind of like end of the line before the empty environment. All right, empty environment is the ultimate ancestor of all the environments. So that's the only one that doesn't have a parent. Okay, and then the base environment's parent is the empty environment. Okay, and then lastly, environment is the current environment. So you type in environment into your R console right now, it'll probably say global environment. Okay. Search lists all of the parents of the global environment. This is called the search path. All right, and so you if you type in search into R right now, it'll probably go. It'll start off with global environment, and then it'll say like package stats, or maybe it'll say like tools RStudio or something like that. And basically it's just or if you've loaded any libraries, those will appear in there. And basically, when you say, I want you to find SD, the function for standard deviation, right? You probably don't have a function in your current global environment called SD. So what it does is it's like, oh, I'm looking for SD. It's not here in the global environment. I'm going to go to the parent environment, okay? Package stats. Inside package stats, I'm finding this function standard deviation, okay? If you look inside the standard deviation function, it's calling on the function variation, right? Variation, so when you run that and you run standard deviation, it's going to run that and it's going to look for variation, and then eventually one of the ways it's like it's calling on this method called like covariance or something. That's how when you ask R, find the standard deviation of this stuff, it's doing a whole bunch of stuff being in the background, right? And one of these things would be finding the covariance, and that's going to be a method that maybe has been programmed in Fortran or something. And so basically what it's doing is it's just going through the search path to find these things. Okay? Yes?
So in this case, if you're looking for a standard deviation, And the package stats and package graphics both have the standard deviation.
It's going to find the stats one first, okay? Because it goes in this order. This is if graphics has a function and stats has a function of the same name, this is the path that it goes, and it's not gonna, once it finds something, it's not gonna keep searching for it. So if you say look for standard deviation and it finds it in stats, it's gonna stop, okay? But if it doesn't find it there, it's gonna go to graphics and it's gonna look for the thing, okay? And if it finds it there, it stops, okay? And so yeah, this is the what the search path looks like, okay? In the global environment, you're looking for something, it doesn't find it, it goes to the next package up, and it keeps going, and it keeps climbing that thing until it reaches the base environment, and then finally the empty environment, okay? But the empty environment's empty, right? So, and then anytime you do library ggplot, library dplyr, whatever, that inserts it right here, okay? It goes right in front of the global environment. So it'll always be the first thing in the search path that goes. Okay.
So between global environment and base environment is just a whole another.
It's all of these. Yeah, these are all parent environments. Okay. So in this display, global environment's parent is package stats. Okay. Package stats parent is package graphics. Package graphics parent is package gr devices and things like that. Okay. So yeah. Okay. So we saw that you can create this thing called new environment using that command new.environment, but most of your functions, most of the time, anytime you have to worry about or think about environments is a consequence of using a function. All right. And so when you run a function, you're going to get these different environments, and there are 4 that we kind of need to think about. Okay, there's the enclosing environment, the binding environment, the execution environment, and the calling environment. Okay, the enclosing environment is the environment where the function is created. Okay, so when you create a function, the environment where it's created is the enclosing environment, and every function only has one enclosing environment. The other ones, the binding environment, execution, and calling environment, you might have one or more, or that might not even be part of the thing. Okay. The binding environment is where the name that calls the function is stored. Okay, or the name that is binded or bound to the function, where that name is, that is the binding environment, right? And then you have when you run the function, it creates an execution environment that where the code is being run, and then and the execution environment is going to be also associated with a calling environment, which is where the function is called. We'll talk about these things. All right. So when a function is created, it gains a reference to the environment where it was made. This is the enclosing environment, and that's where and that is used for lexical scoping. So if inside that function you're calling for variables or other functions, it's going to start in its enclosing environment to start the search path. Okay, so whatever that enclosing environment is, that's where the search path begins. When you name a function, okay, on the other hand, when you name a function, the environment where that name exists is the binding environment. Okay, I'd say almost in most of your scenarios, the enclosing environment and the binding environment are going to be the same. All right, if you write a function in the global environment, okay, the place where you wrote that function is the enclosing environment, which will be the global environment. Most likely, you're going to store that function and name that thing. The thing where you've named it is also going to be inside the global environment, right? So if you want to call it function f, and f resides in the global environment, then f is the binding environment, okay? However, there might be a scenario where you've created this function, but then the name is being stored somewhere else, okay? Then the function resides in the global environment, but the name that is used to call the function might exist somewhere else, okay? And then that would be a situation where the binding and enclosing environment are different. I would say in most of your scenarios where you're dealing with, they're the same, okay? And so, here's a simple example, okay? I'm creating the value y is 1, and I'm creating a function f. And function f is x plus y, okay? Anytime you use the function environment of something, it's going to tell you its enclosing environment, okay? So the enclosing environment of f is the global environment, okay? And this is what it looks like, okay? So we see that the function itself has an enclosing environment, this little black dot. That black dot points to the global environment, okay? So the function's enclosing environment is the global environment. The name f is stored in the global environment, so this function's binding environment is also the global environment, okay? And then so when you run function f and it's looking for value y, it's going to start its search here, go to the global environment, find the value y, see that it's the value 1, and it's going to use that. Okay. Is that okay? Are we confused? All right. The distinction between enclosing and binding environment is important for package namespaces, okay? And so package namespaces will keep packages independent. And so if package A uses the mean function, which is kind of part of the base R thing, and over here you have package B, and for whatever reason package B creates its own mean function. Okay? When you do that, the namespaces ensure that package A, if it ever uses the mean function as part of its stuff, it's using the original mean function and not the mean function that exists in package B. Okay? And so it separates the enclosing environment. So for package A, the functions that might call the mean, its enclosing environment has the search path that goes through kind of the base thing where it's going to find the true thing for the mean. Whereas in package B, you've got the separate namespace, and so even though you have this other thing going on with the different mean, it's not going to mess it up. Okay. I'm going to say 99% of the time you don't have to worry about how all of this works, and just be confident that it does. Okay. So if you, for whatever reason, you decide to create a new standard deviation function, which you are entitled to do, I would advise against it. But if you wanted to do it, you can, but you don't have to worry about your standard deviation function breaking other packages, things that might use standard deviation. Okay, and most of the time it's probably better if you're going to create your own custom standard deviation function. It's better probably to name it something other than the name that exists in the base thing. But R doesn't have, there's only a few reserved words like true and false and null and things like that, so that if you wanted to call something SD, then that's fine. Okay, C is probably one of the most common functions that we use, but if you want to store a variable C, which is very common, it's fine, and it doesn't break other things when you're using these things, right? So you don't have to worry about it. Okay, it works. As far as environments, you do want to think about execution environments. Okay, and so every time a function is called, you get this new environment, and it's called an execution environment, and that's where all of the commands and all of the values created during the running of the function code is stored, and this is where it happens. Okay, and once the function completes running, this execution environment is just thrown away. All right, it's poof, it's gone, everything disappears. All right, so here's a simple, very, very simple function. Okay, it's the function h. Inside function h, we're associating the value to the a, and then we're going to return the value x plus a. Okay, h is a function of x. Okay, and we're going to just return the value x plus a, and we're going to run it by running h of 1, and we're going to store the output into y. All right, so what is y going to be? 3, right? Okay. So this is the picture that happens, right? H, there's a function, okay? Its parent, or its enclosing environment is the global environment, okay? And the binding environment is also the global environment. So h refers to this function. When we call h with x equal to 1, it creates this dotted line area. This is the execution environment. Inside this execution environment, we are passing the argument x equal to 1. Okay. And then, and the first line of code in there is, okay, a is going to be 2, and so that gets created inside this execution environment. And then the last thing is it adds x plus a, so it does 1 plus 2, and it gets the value 3. It returns the value 3 and stores the value 3 in y, and we create the value y inside the global environment here. And that execution environment, poof, it's gone. Right? And that's it, and that's the picture. And so, you know, when you're writing functions, it's important to know that anything that you don't explicitly state as these are the things that should be returned, those values just disappear. And these are separate values. So, you know, if over here we had an x or something like that, this x is separate from the x that happens in the global environment. Okay. All right, and then lastly, let me talk about the calling environment. Okay. When you call a function, it creates an execution environment, right? The execution environment technically has two parent environments, all right? The enclosing environment, which is based on where the function is created, and it also has the calling environment, which is the environment from where the function was called, okay? So most of the time, you're calling functions from the global environment. So in that case, the calling environment is the global environment, and then the execution environment's enclosing environment is also the global environment. Okay, and so those would be the same. But there are often cases where you're going to call a function from inside another function. Okay, and so in that case, the function, like if you have function f, and inside function f you're calling function g, okay? And g is a function that was created in the global environment. Okay, so g exists in the global environment, f exists in the global environment, but inside f you're calling function g. So when you do that and g runs, the execution environment for g has two parents, okay? The normal parent is the enclosing environment, which in this case would be the global environment. Okay, it's the enclosing environment of g, which would be the global environment. But because g was called from inside f, it has what it's also called a calling environment, and the calling environment this time is the environment where f resides. Okay. And it would actually be the execution environment of f, because g was called from that execution environment f, okay, when f was running. Does that make sense? Okay, and so the scoping rules of R says use your enclosing environment, right? So if inside function g, this g was called from inside f, if inside function g it says search for value a that doesn't exist inside here, it's going to start the search for a inside the enclosing environment of g, which is the global environment. Okay, and that's going to be your standard normal case. The scoping rules say start your search with the enclosing environment. So if g is called even from within f, let's say f has its own a over here, but g is called from over here, it's going to start its search in the global environment. There is something called dynamic scoping, however, that says, hey, don't do your scoping the normal way. don't look at your enclosing environment for your scoping, but look at your calling environment for the scoping. Okay, that's called dynamic scoping, and in that case, G will look for A or these other variables starting from the calling environment. Okay, and so things we're not going to probably get into dynamic scoping or what we call non-standard evaluation. Okay, where it now matters where it was called and stuff. Okay, because it does complicate things. It allows you to do some cool things, but it also complicates things because whenever you run a function or you program a function, you now have to think about the function's own enclosing environment and the different scenarios upon where this function might be called, right? And if the function is called from different situations, you're going to have different kind of cases and stuff like that. And so it does get complicated, but that's something called the calling environment, and it allows you to do dynamic scoping. Hadley talks about it in his book Advanced R. You can go into the section non-standard evaluation where it gets into this functional programming stuff. It is fascinating and interesting, and it's used when I don't know, whatever, but it's neat. Okay, but we're not going to get into it. All right. All right. So that's all I have to really say about environments. I don't know if there are any questions or issues on this. We're okay. Sure. Okay, so now let's talk about debugging. All right. So we'll talk about fixing these unanticipated problems and kind of condition handling. All right. And so here, I write not all problems are unexpected. Right. So sometimes you can anticipate where things will go bad. Right. You can kind of anticipate if you prompt the user for input. You can anticipate the user trying to do something that he or she is not supposed to do. Okay, and in those cases you can try to create warnings and messages or things like that. And so so in this case we'll you can create errors using stop. Okay, so stop will just stop the code, it'll quit, and it'll say error. Okay, warnings will allow the code to continue running, but it will generate these messages. Okay, and then messages will also appear. All right, and that's just kind of like to give information about the output, but you can also suppress messages. All right, and so if you use error or if you use warnings or things like that, and they appear in R, they appear in red text. Okay, so like over here, if I say something like print A, it just prints it out like this. Or if I say cat A B C or something like that, it just prints it out like that. However, if I do like 3 plus G, okay, this text appears in red, okay, to indicate that it's an error. And so in your code, if you're anticipating something like that and you want to have like important messages, you can use stop or warning or things like that messages to indicate that it's going to get the red text, or whatever theme you have applied to make sure it appears differently. Okay, it's probably better than using just print or cat, because those are not conditions, and so they just appear and things like that. As far as debugging goes, this is kind of some common sense ideas about being methodical in fixing your bugs. And so it says realize you've got a bug, make it repeatable, find out where it is, fix it, and test it. Okay, so let's just talk about this. And so here's a quote, and it says, fixing a buggy program is a process of confirming one by one that the many things you believe to be true about the code actually are true. And when you find out that one of your assumptions is not true, you found a clue to the location, if not the exact nature of the bug. All right, and so this is you know, it's a good idea to break your code up into manageable chunks, and so you can make sure each chunk of code is doing exactly what it's supposed to do. So as far as your tic-tac-toe game for your assignment, I've kind of broken out, and I've said like here, you know, 4 or 5 functions that you need to program, which kind of breaks out the overall game into separate chunks. And so you can kind of make sure that you know, your display function is working in all of these different scenarios, or that like when the computer is supposed to take a turn, it is doing what it's supposed to be doing. Okay. It says in some situations it might be worth writing 2 versions of a function. Okay, and I think this is true. So if you got code that's working and it's 100% working, great. All right, it might be, the performance might be poor, but you know that code is working. It might be worth having a separate, trying to write a separate function where the code may be more optimal or efficient, but you're not 100% sure if it's doing exactly what you expect it to do. And then you can do some cases to make sure that both things are doing the exact same thing, right? Because if these 2 bits of code are supposed to work in the same way, you can test all of those things. When errors do occur, they often occur at edge cases, which would be the boundary between legal and illegal inputs. So common scenarios for these edge cases are you're giving it a vector of 0 or a missing or a null value or something, or you're giving it really large values close to infinity, or very small values, something close to 0 but not 0. So you know, like if you're using the log function and you give it a negative number, it's obviously going to give you an error, right? But maybe you're giving it very small values. You're trying to do something and you're taking the log of it. And if you give it 0, it's going to give you what? Negative infinity or not a number or something like that, right? And so sometimes you're getting these things that are very close to these illegal inputs, and it's hard to figure out. And sometimes, you know, we wrestle with what is a legal and what is an illegal input. Okay. You know, so I don't know if you heard of like Isaac Asimov's like laws of robotics or things like that, right? And one of these things is like, don't harm humans. Or do you guys know what I'm talking about? This sci-fi writer, right? So it's like, don't do nothing bad for humanity. Don't harm people. You know, don't harm yourself and obey your owner. Okay, and or something like that. Or is it like obey your owner and then don't harm yourself? I don't know, something like that, right? But then there's this thing. It's like don't hurt a person, right? And we think like, oh, it's obvious we know what a person is, right? Or we know what a living person is, and but then there are these what we call edge cases that are complicated, and the answers are, we don't know 100% what the answers are, and so, you know, if you were to kill someone, you obviously would go to jail, right? However, right, there's a lot of questions, right? Like a person who's on life support, who, you know, doesn't have brain activity, is it okay to kill this person? I mean, like pulling the plug, we say pulling the plug on such a thing, but effectively you're killing the person, right? Or you're like causing this person to no longer live, and is that okay? Is that not okay? You know, these are you know, when exactly is a person a person? These are very, they're hard things, and so, you know, governments try to write policies and rules, and I don't know, it's complicated. And you probably don't have to worry so much about these ethical things when we're doing computer programming, but there are cases where you have these edge cases, and it's mysterious, right? Like, well, there's this debate about, self-driving cars, and is the car supposed to kill the owner versus crash into the crowd of people, right? Like, like if I don't know, the car goes out of control and it has the option of driving off the cliff to kill the owner, or drive into the crowd and the owner survives, like, what is the car supposed to do, right, if the car is driving itself? And I don't know, right? Like, anyway, so, what's gonna, anyway, whatever. We'll probably have to worry about negative numbers and not ethical dilemmas. But anyway, okay. Automated testing and just testing in general, right? So it's very normal that as you're writing your code, you do testing, right? Nobody writes 1,000 lines of code and says, okay, I wrote all this code, I hope it works, right? You generally write like 2 lines of code, and then you test it out, and then it works, and you're like, yes, I'm a genius, right? So that's what happens when and so it's very normal to have this very kind of like this immediate feedback system as you're typing out your code, right? You like write a few lines, you just make sure it does its thing, and that's great. Oftentimes, you'll have a function and you want to make sure that it's behaving the way you expect it to behave. And I strongly encourage you, you can do an informal system of testing, but you can make it a little bit more formal by keeping a separate document or something else, or in the comments saying like, when I run this function with this input, it should output this. When I run the function with this input, it should output this. And if I run it with this input, it should output this. And you should think of all of your different scenarios, right? Like, if I'm going to give it negative numbers, it should do this. If I give it positive numbers, it should do this. If I give it 0, it should do this. And think of all of these things, because later on, there might be scenarios where you've had to make a modification, and suddenly this code has broken, okay? And if you just went off the top of your head, you might not remember all of these different edge cases that you had thought of earlier. And so if you keep another document where you're keeping track of all of these edge cases, then you can go systematically and make sure all of these edge cases, all of these scenarios are working properly. You can also automate your coding by writing kind of like other code that says like, that basically runs through a loop that gives it different conditions, and then basically the loop will say like, run the function with this condition and make sure that the output is this. All right, run the function again with this other condition and make sure the output is this. And you can automate that process, and depending on how complicated your code is, maybe that's overkill or maybe it's reasonable to do that. And so I strongly encourage you, especially if you're trying to make sure things are working and you want it to be working in the future if things ever change, write down all of these test scenarios that you want to make sure work, because when you're working in the problem at that time, all of these test scenarios are fresh in your mind and you think of them all. But later on, 2 weeks later, something else changes, and this other code that you thought was working perfectly now suddenly needs to be changed. You want to have all of that about. Okay. All right, making your bug repeatable. All right. Obviously, you want to make sure that the same inputs are giving the same outputs every single time, and you want to be able to make sure you can get the same error every single time under it, and you can know exactly what set of conditions is causing the error. Anytime you're using some kind of randomizer as part of your function, like you're using sample, or you're using R norm or R unif or something like that, it might get harder to make the bug repeatable. All right, and so in those cases, it might make sense as part of your code, rather than inputting the random value directly into the next step, store the random value somewhere into some temporary holder, okay, and then use that as the input for the next thing, okay, and then if under certain cases it works and other cases it doesn't, you might be able to enter the browser, which we'll talk about in just a second, to see exactly what value the randomizer produced. And maybe it's like, oh, it breaks when the randomizer produces negative values, and I forgot. I got to make sure the randomizer doesn't give us negative values or something like that. Identify the cause of the bug. Okay, so we have tools. We've got Traceback. We have the browser. These are ways to make sure the code is working. Or you can kind of identify the sources of error, and then you fix it and test it. Okay, so let's take a look at Traceback. All right, and so here is some very simple code. Okay, I have my environment right now is empty. Okay, and so I'm creating a function f, and this is the dumbest code. Okay. But so function f it's a function of a, and the function f calls g, and it's using a. All right. G is a function of b, and it calls h. H is a function of c, and it calls I. And I is a function of d. And inside function I, it's taking the letter a, and it's trying it to add it to d. Okay. And so if I try to run f of 10, we know that this is going to error out, right? It says error in argument a plus d, non-numeric argument to binary operator. Okay. All right. And so in this scenario, it's very obvious what's going on. We can see that the problem is caused here. But you can imagine each of these things being much more complicated, right? Function f, maybe 50 lines of code. Function g, all of these lines of code. All right. And then when you get this error, you're getting error a plus d, non-numeric argument to binary operator. You might be like, when I look at function f, I don't see d anywhere. I don't see quote a, right? Because you're like, I called function f. I don't see anything that looks like that inside the code for function f. All right? And so Traceback allows you to see the code that gets you to this point, right? The steps that the computer took to get us to this point. And so when we do Traceback, we can see, okay, you started off by calling function f. Function f called function g. G called function h, and h called function I, and this is where we ran into the error. And so now we can say, oh, the problem isn't in function f, the problem is in function I. And then we can look at the code for I, and we say, oh, well, that's dumb. We're trying to add a to d. That's why I'm getting my error. Okay? But so Traceback is very useful, especially if one function or something is calling another thing, and then you're like, f, I've ran function f. I don't know why I'm getting this error. I don't see this code anywhere inside function f. Well, Traceback will say, okay, it's not in f itself. You called g, which called h, which called I, and so the problem lies in I. Okay, and so that's what Traceback does. And so you can, when you run it, you can just click Show Traceback, or you can do Traceback this way. Whoops, and it shows you exactly the exact same thing. All right. So Traceback, it often helps us identify, when there's problems in the code and things like that. Right. Okay. The other tool that we have is the browser. Okay. So a lot of times when like I said, when you run code, it creates an execution environment where all of the values are stored, and then when the code finishes running, it sends that back as results, okay? Or as returned results. And then so if you want to know what is happening inside that execution environment, you can use the browser, okay? And so here, are you guys familiar with a bubble sort? Yeah? Okay. So bubble sort, the idea here is like we're going to sort some numbers, okay? So here we want to sort the number, this vector of values, and what it does is it takes two values, it compares it. If the left number is bigger than the right number, it's going to swap positions, okay? And then so as it does this, it's going to keep swapping, and then eventually it's going to get the 8. The 8 is going to move all the way to the largest spot, okay? Because at this point it's going to say, oh, the left is smaller than the right. This is here, and it keeps doing this. And then so the 8 gets pushed all the way over there, and then it keeps going through, it cycles through the whole thing again, and it wants to do that, okay? So here, if you wanted to use the browser, okay, you can you can just click little inside the your code. You can click on the boundary over here. This creates a breakpoint, okay? And then so now I'm going to look at x. X is this vector 263415, and we're going to call bubble sort on it, okay? And then so I've created a breakpoint at this point for if this, all right? And so I'm going to run bubble sort on x, okay? And it's going to start the code, all right? And we can see the environment here. This environment is no longer the global environment. It is now the environment, the execution environment for bubble sort. There are only three things here. We've given it x. This is what we've passed into the argument here, x. And we have the value I, which comes from this loop. And then we have the value j, which came from this loop. Okay, so we have 4 loops inside each other. Okay, and so we have the value I, j, and then we have the values x, okay? And then so far nothing has happened, and we're about to execute this code here, right? And we're going to say, okay, we can look at exactly what x sub I is. We say, oh, that's 2. And we can go x sub I plus 1, and we say, oh, that's 6, okay? So the if statement is x sub I greater than x sub I plus 1? And what's the answer there? The answer is false, right? So in our code, we can just click next, okay? And so it looks at this and it says, okay, it didn't do anything there, all right? And so because that was false, all right? And then so we just click next, and then so now it's going into the next part of the code, all right? It goes back to our for loop, and we can see that I is now at 2, okay? And so we can see, okay, well, what is x sub I? All right, it's 6, and x sub I plus 1 is 3, and we can just see the next line of code, okay? And so, oh, it's doing it's activating our browser here, okay? And why is this? Okay, so it's running here, and then so now it's going to go into this step here, and it says, okay, we are going to run this code, all right? And so you can see that hold will get created here, okay? Hold is going to take the value 6, okay? And then and it's swapping these things here, okay? And so now x now is 236, okay? And we can run line by line by line into these things, or you can hit continue, which keeps running until the next breakpoint is encountered, which, because mine is at the top of the loop, it will run. And so you can kind of see step by step how I and j's increment and how this is affecting our x variable here. All right, and so this allows you to kind of see each of these things here, right? And so now j is 5 and I is 2, and you can see how the things go. And so browser allows you, or by setting breakpoints in your code, it allows you to step into the execution environment and see exactly the values that are being processed, okay? And so when you're running into problems and you're getting unexpected results, it might be useful to step into the execution environment and see exactly, is this value what I want it to be? Is it doing what I'm expecting it to do? And then you might say, oh, this is where something is going wrong, okay? Okay, and so we'll stop there.